Hi, welcome to a new lecture in the module Optimization for Machine Learning. This module is part of the course Foundations for Machine Learning, and today we'll be looking at momentum to make better gradient descent. So in this particular module, we have been looking at various ways to implement gradient descent. In the previous lecture, we looked at stochastic gradient descent, and today we'll be covering momentum. There are two more methods that I want to cover in this module. The third one would be RMS prop, root mean square propagation, and the last one would be Adam optimizer, which is the most famous optimizer usually used in machine learning. So don't worry if you don't know what is gradient descent. I'll be covering that as a recap in the first part of the lecture. So I have structured this lectures in two parts. In the first part, I'll be covering the theory behind the momentum for gradient descent. In the second part of the lecture, we'll be implementing this by code so that you can see why momentum is good to have compared to vanilla gradient descent or compared to the normal gradient descent that we usually do. So let's get into the lecture. So gradient descent is nothing but something that you use to minimize loss function in machine learning. Loss function is an index, or it's a measure of how far away your predictions are from the actual data points. So if loss function is denoted by J and the ML model parameters by theta. So when I say ML model, just imagine linear regression, fitting a straight line through a bunch of data points. The parameter is slope and intercept. Loss function is mean squared error, which is how much the points are deviating from the line. You square those errors and you take a mean of that. So that's mean squared error. So in gradient descent, what we do is we first start with some random value of parameters in the very first step. And when I say random value of parameters in the context of straight line, it's random value of slope and random value of intercept. Then we keep on iterating to modify this theta such that finally we can reach a value of theta which will minimize the loss function. That's the entire goal of gradient descent. So the first step is starting with random value of model parameter, which I mentioned. Second step is calculating the gradient. So this term is the gradient. So this is gradient of J, which is a function of theta with respect to theta. So you are taking the gradient of the loss function with respect to parameters, and then you are multiplying this with a learning rate, and then you update the parameter in step 3 by saying that the new value of theta equal to old value of theta minus learning rate times the gradient of loss. Then you repeat these two steps, calculation of gradient and updating the parameters, how many ever number of times until you are satisfied with the level of reduction of loss, or you will do this for a predetermined number of iterations. You can call it as a point where you are happy with the level of convergence. Now the problem with this kind of gradient descent, which is the normal gradient descent, so there are several terms. This is also called vanilla gradient descent. It's also called gradient descent. It's also called batch gradient descent, because here you are using every single data points to calculate the gradient loss. So here actually, if the J, which is the loss function, is defined as mean squared error equal to 1 by n times sigma y predicted minus y actual ith value the whole square. So this is the mean squared error, and here this I runs from 1 to n. So it uses all the data points that are available. And this is fine if the value of n is small, but imagine if the value of n is 100 million data points. It's very computationally inefficient to calculate the error for every single data point and then calculate the gradient. So it's very difficult to perform fast calculations, and convergence is also difficult on noisy loss surfaces. And when I say noisy loss surfaces, I mean loss surfaces where J is this, theta is this, and things can look bit jumpy. So this is where we have to figure out ways to make gradient descent better. In the last lecture, we learned how stochastic gradient descent makes the gradient descent slightly better. In this lecture, we will see a concept called momentum and how it makes gradient descent better. So momentum, when you hear the term momentum, I'm sure you are thinking about the momentum from physics, and maybe you are wondering, oh, maybe that momentum is not related to this momentum. But don't worry, this is exactly same momentum, meaning this concept of momentum is directly inspired from physics. So the idea is this: in the gradient descent, when you are making updates, add an inertia term. You might be wondering how to picturize this. I will definitely help you picturize this when we are plotting a graph, and I will help you understand why are we calling this as inertia, where exactly is this momentum coming. But for now, just understand that the value of the parameter optimization, that parameter optimization term, which is theta minus something, the value of that term, instead of taking it to be just the gradient, we will modify that term a little bit. So you will see how exactly that modification is done. The goal of this is that you can avoid oscillations that can happen sometimes during gradient descent process. So let's say this is your loss function and this is your theta parameter and this is your loss function shape. Then depending on the learning rate, in vanilla gradient descent, you can come to here. Then if your learning rate is too high, okay, maybe you can start from here, you may go here, you may go here, here, here. You can have ever increasing values of losses and reaching absurd values. I will show you exactly this, where the loss, the j of theta value reaching like huge absurd numbers, like I don't know, 10 raised to 50, 10 raised to 34, numbers like this. I will show you this during the implementation in code. So momentum will help you first dampen these oscillations in steep regions, and momentum will also help you maintain certain direction in flat region. And what do we mean by flat region? Whenever we say region, flatness, steepness, imagine it all to be steepness or flatness of the j curve with respect to theta. I am drawing it in just 2 dimension, but understand that theta has multiple, there could be, let's say, slope, intercept, and there could be n number of dimensions, but I'm just calling it as theta. Now just understand that when I say flatness, it is the flatness of this, of the loss function. When I say steepness, it is the steepness of the loss function. This is steep, this part is steep, and this part is flat. Now in the flat portion, can you guess what is the issue in the normal gradient descent? Here the gradient is very small, it's almost 0. And because of that reason, the updation of the parameter will happen so slowly that you will spend a lot of time in this region. But if momentum is there, if updation is happening fast in this region, that speed or that inertia is carried forward, so that here also updation can happen faster, so that your gradient descent can proceed in this direction, right? So you will see this in much more clarity when we implement in code. So the idea is that combine the previous update value, the previous velocity, with the current gradient to smooth the optimization trajectory, rather than slowing it down at flat regions or completely making it fast and diverging or oscillating due to the steepness in the steep regions. So this is the idea behind momentum. So let's first discuss the mathematical representation of momentum, and then after that we can implement this in code. So firstly, we introduce a term called velocity. Velocity is an index of momentum. So if you are considering a particle of unit mass, its momentum is same as its velocity. Now this equation that you see right now is not the equation where you are modifying the parameters. The parameters are not coming into the picture yet. This is just the equation where you are calculating something called as velocity. Don't worry if you don't understand what this velocity is, but just stay with me for a moment. So all that this equation is trying to say is that the current velocity, which is velocity at time step t, is equal to 99% of the previous velocity, 99% or 90% depending on the value of beta. Current velocity equal to, it's pretty much equal to the previous velocity, but we are adjusting it a little bit based on the current gradient. So current velocity equal to previous velocity, it's 99% previous velocity plus a small fraction of the current gradient, right? So that is what this equation means logically. And how is that being implemented? Don't worry if you don't understand what this Vt minus 1 is, you will come to know that. But just understand this much: the velocity at a given point is calculated such that it is almost equal to the previous velocity, but there is a minor 1 minus beta term. So if it is beta is 0.99, 1 minus beta is 0.01. So 0.01 times the gradient. This is the velocity term. Now, what are we doing with this velocity term? We are previously here in this equation, we had gradient of theta, loss function with respect to theta. So we are replacing this term with the velocity term. So essentially what we are saying is that we are updating theta using a learning rate and of course using the gradient also, but gradient we are not directly using. Instead we are using something called as velocity. In the velocity, the gradient is embedded in this form and only a small fraction of the gradient is used. What fraction? Maybe 0.1 times the gradient is used. Remaining 0.99 fraction is the weighted. So you're taking a weighted average of 0.99% of the previous velocity plus 1% of the current gradient to get the current velocity, and you're using this velocity to update the value of theta, right? To me, it makes a lot of physical sense. I can perfectly imagine this, but and I wish you can also imagine this thing in a logical way. It is okay if you cannot imagine this in that physical sense. It's okay, but I'll be so happy if you are able to do so. Just let me know if you are able to visualize this as a something like from a physical point of view. If not, it's fine, right? Because these are anyway simple equations. Now let's think about why this is very useful, this way of updating the parameter theta. Imagine the case where gradient is 0. So let's say your loss function, for some reason it is in this shape, this shape. So the gradient is 0 in this region, which means if we were having, instead of Vt, if we were having a gradient of j like this entire term is 0, which means theta is not going to get updated, and x-axis is theta. If theta is not going to get updated, it will stay here forever. It does not matter if you are running 1000 or 10,000 iterations. But so in flat terrain, updation will instantly stop in the vanilla gradient descent. However, in the case of momentum, the updation will not instantly stop. And why is that the case? Because the Vt term does not become 0 even if the gradient is 0. So in the flat region, although this term is 0, this gradient term is 0, the Vt term is actually only 1% of the gradient term. Remaining 99% is it's the previous velocity. So, and what is the previous velocity? Let's say previously the value of theta was somewhere here. Then previous velocity is corresponding to the velocity before that, which is here, plus a small fraction of the gradient at this location. So although the current gradient is 0 over here, it is fine because you can still update the value of theta because Vt is not going to be 0. But if we just use vanilla gradient descent, the gradient of j will be 0 and theta will be stuck there forever at the place where the slope is 0. Now this extreme case is when the slope is 0. This also applies if the slope was a very small number, then the updation in theta will happen very slowly and you will have to wait forever for you to reach a minimum value of loss. So this is one issue which the momentum can solve. Now if the slope is steep, momentum keeps increasing. So what does that mean? What that means is this. Imagine that your loss function with respect to theta is like this. Wherever the slope is high, so ideally if a ball is rolling, right, it's not coming at going to come down at a constant velocity. Its velocity will keep on increasing because it's accelerating. Similarly, so it means that you want to update the value of parameters. If you want to mimic these physical systems, you can update the parameters at an ever increasing faster rate, and you can do that only if you are accumulating the gradient from the previous steps, because in the previous step there was a good slope. Now there is a slightly smaller slope which does not mean that you have to slow down. If you remember how vanilla gradient descent works, it actually slows down, which is very different from how in actual physical systems things work. So if you are rolling a ball down this ball is always experiencing a force in this direction except for here. So this ball's velocity is keeping on increasing if friction is not there. So in the first time step, the ball will cover distance from here to here. In the next time step, it will cover from here to here. In the next time step, it will go from here to here. In the next time step, it may reach over here, right? This is how actual physical systems work. So you can perform this kind of an updation of theta. So imagine this was J and this was theta. And here theta is getting modified very little, here even more, and here even more. You can do this only if the value by which theta is updating, which primarily depends on this term, if that term itself is increasing in size. And it indeed increases in size if you are using velocity, where you are accumulating the previous velocity with the current velocity. On the other hand, if you are using vanilla gradient descent, where this velocity term is not there or momentum term is not there, then you have J, theta. Initially you have a big slope here, which means you are taking a big jump from here to here. Then you are, let me draw a bigger jump from here to here. Then here the slope is lesser, so the value of jump is lesser. Here again the slope is less, value of jump is less. Again the slope is less, value of jump is less. So this is as if the ball is slowing down, but in physical systems this happens if the loss function was like something reverse, like let's say it was climbing up, then yeah, the ball can, if you are giving the ball a very good push, then it will be fastest here, and by the time it reaches here it will slow down significantly. So this is opposite to what physical systems look like. And the value by which the theta gets updated becomes an ever decreasing smaller and smaller number. You see this becomes smaller and smaller. So it slows down significantly. In momentum, on the other hand, it becomes faster and faster. So this is one advantage, where if the slope is steep, the momentum keeps increasing. This we already discussed. And the final thing is, due to inertia, it's very difficult to instantly flip the direction of the gradient, which happens in the oscillations. So what does this oscillation mean? Oscillation is nothing but this is J, which is loss function with respect to parameters theta, and let's say this is the loss function shape. I keep on drawing this parabola because it's the easiest thing to use for explaining loss function. Now imagine that you are here and you are taking the slope, and you based on the slope you are going in this direction. But the distance by which you will move will depend on the learning rate. Now imagine your learning rate is too high. Then you will jump from here and maybe you will end up here if your learning rate is too high. Then from here you have a positive slope, which means your theta is equal to previous theta minus some positive number, because the slope is positive, which means theta will decrease. But theta will decrease by such a big extent that you may end up reaching here in theta. So theta can go from this value of theta all the way till this value of theta, which means you are going here. Now because slope is negative, you will have a negative of negative number. So previously this was a positive number, now you have a negative of negative, which means positive. So you're adding now some other from some higher value to theta, so you will reach here. So essentially what you're doing is you are oscillating. You're going to higher and higher values of J if you are using vanilla gradient descent. Now imagine we are, instead of using vanilla gradient descent, we are using momentum. So this is J and this is theta. So over here, even if the learning rate is high, over here you have a certain value. So let's say you're starting from here, you acquire a certain velocity, you will slowly start, and let's say due to the big value of learning rate you ended up over here. So here, although the gradient is positive, so here the gradient was negative, here the gradient is positive. So although the gradient is positive in this case, the updation of theta is theta minus some number, and this number is the velocity term Vt, and Vt is 99% Vt minus 1 plus 1% current gradient. So although the direction of gradient has flipped from a negative to positive because the theta moved from this value of theta all the way till here, the updation of theta will still proceed in a certain direction, such that because now the updation of theta is not affected just because the gradient has flipped, because only 1% of the gradient is contributing towards Vt, remaining is about Vt minus 1. So this can in effect avoid the oscillations, which you can visualize when we implement the momentum in Python. So these are some advantages of momentum. It's fascinating actually. I absolutely love this concept because I'm sure whoever thought of this for the first time probably thought of some physical system analogy. I mean, I'm sure it requires a lot of abstract thinking skills which involves math as well as physics, but it's fascinating to me to think about the person who might have thought of this for the first time. It's really, really beautiful. So let's now implement this in Python completely from scratch. So as usual, to save some time so that this video is not too long, I have written the code. I have tested this already, but I have divided it into different, probably meaningful chunks. So I'll first explain the logic behind the code before implementing it, so that while implementing you can understand the reason behind different blocks of code. So first is obviously importing different libraries. So you have NumPy for dealing with arrays, and you have matplotlib for plotting the graph of loss versus epochs and other plots, and we are defining the loss function. So in the case of stochastic gradient descent, we were not directly defining the loss function. We were defining data set, and then the loss function was just happened to be mean squared error, because on the data set we were planning to perform a linear regression, so we were using mean squared error. But here we are saying that the loss function j is taking a form that looks like this: x square plus 10y square. So like a equation of an ellipse. So something like that, right? It's not exactly, but it's like, so equation of ellipse is let's say ax plus by. If you look at the gradient of this, it will look like elliptic circle. So this will have 3 dimensions. So the shape of this function will look something like from the top down, it will look like a parabola, concentric ellipses. But if you look from the sideways, it will look like this in 3D. It will have all directions. So this is the quadratic loss function. So we are basically not going to define data set x and y. Because this x and y is not data set. This is simply the parameters that the parameters that define the loss function j, right? So j of theta. So this is j. The output, this whole thing is j, and these are thetas. It is not the input and corresponding output. Please understand that. We are not defining the data set here. We are saying that somehow we happen to know that the form of loss function is like this. It's fine, I mean, because we just want to demonstrate a point here. So this is the quadratic loss function. Now the gradient of the loss function is, we need to do dou by dou x and dou by dou y. Dou by dou x, if this is 2x, dou by dou y is 20y, right? So that is dx and dy, because we need gradient to calculate the momentum. Now batch gradient descent is the normal gradient descent that we do. So we start with a particular starting point x comma y. Starting point we can input into the function. So this is the batch gradient descent function that we are writing. And what we are also doing here is, like, we are defining a variable called path, so that we can keep track of where we are in terms of parameters on the contour that defines the loss. So this path is a variable where we'll be storing the different points of x comma y pairs. So x comma y are parameters theta. It is not input output. It is parameters theta for j of theta. Path is basically the collection of values of theta at initial time point, theta at the next time step, theta at the second time step, etc. So we are appending the path after each iteration. So just understand that. And then the losses we are calculating based on the quadratic loss. Where is quadratic loss? Here. This is the loss function, right? Or this is fairly easy. Now what we are doing is, we are running for whatever number of epochs we are defining. So first we calculate the gradient. So gradient is called grad. Where is that grad function? The grad function is nothing but whatever we are passing into the gradient descent. And what are we passing into the gradient descent function? It's written down here. Into the gradient descent function, wherever we are calling, we are passing the quadratic grad function. Quadratic grad function we had defined over here. dou by dou x to be 2x and dou by dou y to be 20y, right? So that is this. So it calculates the gradient for that particular shape of grad x square plus I think it's 10y square. For that function, this calculates the gradient for the x and y points which we are using at that point of time. Then and what are the x and y points? They are the parameters. Now we are updating the parameter x and y such that, and see, this is minus equal to, meaning the way you can write this is x equal to x minus eta times grad of 0. So grad of 0 is the dou by dou x and grad of 1 is the dou by dou y, because this grad consists of it's returning an array consisting of the derivative along x direction and derivative along y direction. And then we are appending the losses so that we can also plot loss as a function of epochs. And then we output the path, meaning the array consisting of theta at the first time step, theta at the second time step, etc. And we are also returning the losses to wherever this function was called. So this is the normal gradient descent. We know this is the batch gradient descent, normal batch gradient descent or vanilla gradient descent. Now gradient descent with momentum is here. So we start with some point, we know that. We start with 0 velocity. So at the starting, when a ball is starting to move, it is starting from rest, right? So velocity at the starting is 0. The path, the initial point where you start from itself is the first point in the path, and then you are later appending over here. Then losses is obviously quadratic losses for the first starting point. Then you are again running a for loop for whatever number of epochs you are passing. So first you calculate the gradient, then you calculate velocity in the next time step to be the sum of 99% of the previous velocity or 90% of the previous velocity, depending on the value of beta, plus remaining 10% or remaining 1% of the gradient itself. And then you modify the value of x and y, but this time you are not modifying with respect to grad of 0 or grad of 1. You are modifying with respect to v of 0 or v of 1. This is momentum in x direction and this is momentum in y direction. Previously we were looking at grad of 0 and grad of 1 for the batch gradient descent. So that's the only difference between batch gradient descent and momentum gradient descent. And then obviously we append the losses so that we can plot the loss as a function of epochs. Then we return the path, which means the parameters x and y for time step 1, time step 2, etc. as a one single array, and we also return the losses. Now visualization. So we are plotting. The visualization part is simply plotting, and you will see what exactly this plot looks like once I run it. I don't want to go through the visualization part because this is not a data visualization course, but more like I want to focus on the math part of the gradient descent, which we have covered. Then this is actually not loss, this is visualization of path, and finally visualization of losses. So this is the whole set of different functions that does our work for us. Now we have to call these functions. So first we will define the parameter. So eta BGD is eta for batch gradient descent equal to 0.1. This is the learning rate. Eta momentum is eta in the momentum based gradient descent, MGD. I will write it. Just momentum itself is better. This is also 0.1. Beta is nothing but the term that we use for saying, oh, whether you want to use 90% of the velocity, previous velocity, or 99% of the previous velocity. So that is this term, 0.9. Then number of epochs is 50, and starting point, some random starting point. And what is the starting point? It is starting point in the landscape. So we have x, y, and here is the loss function. So, and then we are saying that, so this loss function will look like a parabola. It will have all dimensions, like 3 dimensions, but basically the equation is j equal to x square plus 10y square, right? So this is the format of the loss function. So x and y are parameters if they are not input and output. And you are starting from x equal to 1.5, y equal to 1.5, and hoping that you will find the minimum value of this function, which happens at, you know very well where the minimum happens. The minimum happens when x equal to 0 and y equal to 0. So finally this is where you should reach, right? And then you run the batch gradient descent function, you call it with all the gradient function, the eta, which is the learning rate, number of epochs and starting point. You do the same with the momentum gradient descent, and finally you plot the results by calling the plotting the path function and plotting the losses function. Alright, fairly straightforward. I don't have to spend individual time on these individual lines. It's because the logic is very clear, I hope. Now we can implement this code. I'm going to do this in Google Colab, and as usual, feel free to follow Google Colab or Jupyter Notebook or whatever you like to use. So let's open an empty Google Colab notebook. So here is our Google Colab notebook, and now we can start with the first set of code, importing the libraries, then defining the quadratic loss function x square plus 10y square, then defining the gradient of this function along x and y direction, so dou by dou x and dou by dou y, which will be 2x and 20y respectively. Then the function for performing vanilla gradient descent, aka batch gradient descent. Then the function for performing gradient descent with momentum. We are still not calling the function, we are simply defining it, so there won't be any output yet. Then the function for plotting the paths, and when I say path, it is simply the value of theta at every single time step. Again, we are just defining the function. Only when we call we will get some output. Then the function which will allow us to plot the losses as a function of iteration for both of these methods. Then definition of parameters, the learning rate in both cases, epochs, and where you start. And here is where the main operation happens, calling the batch gradient descent function and calling the gradient descent momentum. But even after running this, you will not see any output visually because they are all stored in this variable. So we have to plot from this variable. So we already got it. We already got the results. Now let's plot it. So path BGD is the path from the batch gradient descent. Losses BGD is the losses as iteration wise losses from the batch gradient descent. And same thing for momentum, the path and the losses from the momentum gradient descent. Now let us plot the results. So first we are going to plot the paths, and let us run. Now here, this is a very interesting plot. I'm not going to tell you for a moment what exactly this plot is. Can you take, maybe you can pause the video here and think what this plot is. I don't have to pause, right? Because I can directly explain. If you want, you can pause. But basically, this is a plot showing. So what was the equation? Our equation was x square plus 10y square, which means along the y-axis, it will look like an ellipse elongated along the y-axis, right? So here we are looking at contours where the loss is constant. So these are like those contours, those what is it called, equi or iso. There is a term for this which I am completely blanking, but basically lines along which the value of loss function is constant. So those are, it will look like an ellipse. This will look like a circle if we were having a function, loss function like x square plus y square, then it will look like a circle. But it will, using circle, we won't be able to show this point. Now, ignore this blue zigzag line and this orange random curve. Ignore it. What are we trying to do? Plot. We are trying to plot the path that the parameters took. Meaning, we are plotting the values of x and y at every single time step for two different methods, one for batch gradient descent and one for momentum based gradient descent. So let's look at batch gradient descent first. In batch gradient descent, there is no concept of momentum. So the way in which the parameters will get updated will not resemble the way in which a ball is moving down the contour. Now, is the ball moving from here to here? Because see, this is the movement of the ball when you are looking from top to top down. So actually what we are plotting is, you are looking at this graph, the contour is in this shape, and you are looking at from top to here, and we are plotting that. So the ball is actually rolling down the contour like this, but you're plotting it as if you are looking from here. Okay, so so here the blue does not look like a ball is going down the contour into the bottom part of this kind of like this parabolic shape. That the blue does not look like that. And why is that so? Because in this case, as I showed you in the example, it is possible for the momentum to shift instantly as if the ball is being hit by like an impact, right? Whereas in the moment, so we are starting from a starting point. Starting point was x equal to 1.5, y equal to 1.5. Remember that we had defined it over here. So that is exactly the starting point, this green starting point. Starting point is the same for both cases. So x equal to 1.5. So here x axis value is 1.5, y axis value is 1.5. And the ending point, ideally, because we know that the loss is minimum when x equal to 0 and y equal to 0. So ideal ending point is over here where x equal to 0 and y equal to 0. And you can see that the ending point for the case where momentum is there, where the parameters theta, which is x and y values, are getting updated very smoothly like this. You can also see this gradient descent with momentum. There is a nice GIF which you can where can I see that momentum 3D. There was a very nice GIF somewhere I had seen on, maybe it is this. Yeah, I don't think this is the one. Something like this. So it will look like this shape, and then if there is momentum, the ball will go very smoothly, or the updation will happen very smoothly. Excuse me. And one more thing, here actually there is convergence, because this orange curve started at 1.5, 1.5 and it finally ended at 0, 0. On the other hand, I think the ending point for the bash gradient descent is over here, where it has not converged onto 0, 0 yet. So we will see this when we also plot the loss. So let me close this and let me plot the loss, not just the path. So when we plot the loss, you will see that the loss for bash gradient descent, see, it is high, it's something like 10, and the loss for momentum based gradient descent has come close to 0. But sorry, not 10, the loss is something like 22.5. I'm sorry. So this is close to 22.5. And can you tell why this is close to 22.5? Because the loss we have defined to be x square plus 10y square. So here x value is 0, right? So the final value where this guy has ended up is here for the blue, meaning for the bash gradient descent, the final value of parameters are x equal to 0 and y equal to something like 1.5. So basically the loss should be 10 x square plus 10y square, where x equal to 0. So it's basically 10 times 1.5 square. So 10 times 1.5 times 1.5, which is 22.5. And isn't that the value of the loss? See, this is 22.5, the final value of the loss. So this is the interesting thing about difference between using bash based gradient descent and momentum based gradient descent. I want to show you one more thing. Maybe we can play around with the momentum a little bit. So let me increase the momentum to 0.2 in both the cases, and I want to show you something that will blow your mind. So see, you know that when the learning rate is high, did I say momentum previously? I meant to say, if I did, I meant to say not momentum, I meant to say learning rate. So the learning rate for bash gradient descent to be 0.2, and learning rate for momentum based gradient descent also to be 0.2. And you see what's happening now. Now the x comma y plot has all those circles of the ellipses have vanished, because the bash gradient descent has completely gone haywire. See, now the y value is 10 to the power of 24 and the loss is increasing. So this is similar to the case where oscillations are happening. So the bash gradient descent is not converging. Instead, because now the learning rate is very high, is jumping to higher and higher values of losses. So now this is like 10 to the power of 49, a huge number, right? And we have only increased the momentum by a little bit. On the other hand, the loss for I think the actual value of loss, maybe we can plot losses momentum. I hope it is very close to 0. So let me plot the actual value of loss for the momentum. See, it is very close to 0, 0.016. And the reason for that is, if we plot the path, hopefully the final value of the path should be 0, 0, somewhere very close to 0, 0. It should start from 1.5, 1.5. See, 1.5 comma 1.5, and final value is close to minus 1 times 10 to the power of minus 1, which is minus 0.1, and this is minus 0.02. So it's very, very close to 0. Both x and y values are very, very close to 0. Very good. So this is the difference between so in this case, basically what I'm saying is, although the learning rate, number of epochs, everything was exactly the same for both momentum based gradient descent and batch gradient descent or vanilla gradient descent, the vanilla gradient descent, instead of converging, it diverged and became so huge to absurdly big number of loss. And on the other hand, with the exact same parameters, momentum based gradient descent converged. So this is the point that I wanted to convey. We can do one last experiment. Let's play with the lower value of the momentum, and you will see the difference. So if it's a lower value of momentum, of course batch gradient descent will also converge, but it's converging in a different way. See here, now oscillations are not there. Batch gradient descent is converging fairly. I mean, it has not converged to 0,0, maybe because number of epochs we have to increase. So I'm keeping 150 epochs, and now it should hopefully converge to 0,0, both of them. Yeah, see, so this time this guy came directly here. I would say batch gradient descent was more efficient. The vanilla momentum based gradient descent oscillated a little bit, but that is fine because momentum based gradient descent works in all cases. But batch based gradient descent worked in this particular case because the learning rate was small. Basically, when you are saying the learning rate is small, essentially you are saying that you are only updating the values of theta by only a little bit in every iteration. So I hope this brings a fairly good amount of clarity to you regarding batch based versus momentum based gradient descent. I absolutely love these plots because it tells a story. I mean, if you look at this plot without any context, probably you will not understand. That has happened to me in the past. But if you look at this plot from the point of view that batch gradient descent is not like a physical object moving down a terrain, whereas momentum based gradient descent will resemble it to a close extent, then you can appreciate this plot better. So maybe this is a good time to wrap up the lecture. So the conclusion that you should ideally have is, in cases where divergence happens in batch based or vanilla based gradient descent, momentum can bring convergence. It's very, very efficient. You are not running, you are considering all the data points. Unlike the stochastic gradient descent, you are not discarding any points. You are using every single data point, but you are using a different approach to perform updations to the values of theta. So here is a visualization of the momentum based gradient descent as a GIF. It's available in Google. Basically, you can see that the way these balls are moving, it's like, this is exactly how a ball will move physically according to physics. You can see that it's following some kind of physics, and the way, if you trace the change in parameters, basically tracing the path of theta, this is exactly what's happening to the theta in the case of momentum gradient descent also. So in this case, you can assume this grid, this contour to be that of a loss function, and the xy are the parameters. We also had a function like x square plus 10y square, and by the way, in this GeoGebra graphing calculator, 3D calculator, you can visualize the x square plus y square 10y square function. So x square plus y square would look like this, like a proper parabola. So from the top it will look like this. I hope we can display the iso contour somewhere. I'm not sure. Probably does not matter. Even if we cannot, it's fine. And if it is x square plus 10y square, it will look like a ellipse from the top. So you see, this looks like an ellipse elongated along the y-axis. So but anyways, so I just wanted to show you this, but we have, I hope this diagram brings you a fairly good clarity. So these ellipses are nothing but these top down views at different points of x at different iso contours. Yeah, iso contour is the value, is the term. So I hope you understand fairly well why momentum. I mean, it's a simple concept. I wish, you know, everyone could visualize the way momentum works in terms of tracing the contour of the loss with respect to the parameters. But I hope at the end of this lecture you fairly well appreciate this idea as a whole. So I think it's a good time to stop this lecture, and as usual I would love to appreciate you for taking your time to reach till this point of the course. You are already ahead of most of the people, and I'll see you again in the next lecture. In the next lecture we'll be covering RMS prop, root mean square propagation, and in the following lecture we'll be covering Adam optimizer. So take care until then. Thank you so much. See you soon. Bye.